Hello dear students, welcome to week 2 of the NPTEL course on solar terrestrial physics. We will continue our discussions on sun and interplanetary medium or interplanetary space. So far, we have understood what exactly is solar terrestrial physics, what and all are the areas of uh, or topics that this course will cover, and what are the pillars of this course. In order to make a successful transition from the solar prominences or solar eruptions towards the Earth or the interplanetary space, we should first understand what and all constitutes the solar prominences and how Sun as a star or as a magnetized body is responsible for the creation of these coronal mass ejections or solar flares, etc. So, in this lecture, we will try to understand more interesting or more relevant aspects about the sun, which are needed for the understanding of solar activity. Okay, so we call it as the active sun. So, sun is not sun doesn't emit the same amount of energy at all times. Luminosity of the sun is nearly constant, but there are slight fluctuations, and these fluctuations have a periodicity. In the sense, these fluctuations will be maximum at certain point of time, and then they will come back to minimum, and this goes on like that. So, as a result, what it means is that sun has an activity period which we call as the solar activity or solar cycle. Okay, so the activity or the periodicity that is associated between this maximum and minimum is 11 years. The periodicity is the time period over which things will repeat themselves is 11 years. So, in the picture, what you see is the image of the sun taken at 30 nanometers. What you would notice is that it's not the same, right? The three images which are spanning between 1996 June to 1999 December, so which span over this period of time, almost 3 years of time, what you see is the sun is not the same. So, first in the beginning, let's say we call it as 1. In 1, sun looks to be quiet, or more importantly, there are no visible fluctuations on the sun. So, everything seems to be uniformly distributed. So, what you are seeing is the photosphere, but you are seeing in a different wavelength. That's why it will probably look, it doesn't look yellow. Okay. So, what you see is a uniform distribution of the intensity of light, or the photosphere is entirely uniform. But as you move in time towards the right, the sun in this 1998 image, you see that there are bright regions which are, of course, which are identified here, which are easily seen here. These are the bright regions which are popping out of the image, which are disturbing the uniformity of the intensity over the entire visible disk. Right. Even if you move further towards the 99 December, you will see that many of the prominences are clearly visible on the sun. That means the ejections, the solar coronal mass ejections are clearly visible from the sun. You also see these solar flares, and much of the, if you right now, if it so happens that if you can have a total solar eclipse, the entire corona and the solar wind outburst can be clearly seen in this image. So, what does it mean? It means that sun becomes very active at certain point of time, and at the same time sun is very quiet at some other point of time. So, this change is not something which will linearly progress, rather it has a periodicity. Things will repeat themselves in the periods of 11 years. So, this activity period is called as the solar activity. Now, if you want to understand, like I said before, the differential rotation of the sun, wherein the equatorial region is rotating very fast in comparison to the polar regions, is responsible for the creation of all the solar prominences. This is what we have underlined in the very beginning of this course, right? Now, in order to understand how differential rotation is responsible for the creation of solar prominences, right? We should understand, or we should start treating the sun as a magnet. Okay, so differential rotation in combination with the solar magnetic field leads towards the formation of the solar prominences and subsequent phenomena. Okay, so let us try to understand how sun can be treated as a magnet, or what is the true nature of the solar magnetic field, sun's magnetic field. Right. So far in our discussions, we have not talked about the magnetic field of the sun. We have looked at the physical characteristics or physical parameters of the sun in terms of its mass, density, temperature, energy transfer mechanism, so on and so on. Right. So magnetic field, of course, sun is a magnet. Sun has a magnetic field. So sun's magnetic field is produced by the flow of electrically charged ions and electrons. Quite straightforward, right? So moving current, of course, will lead towards the creation of magnetic field. So the magnetic field strength and I, the current, are directly proportional. Right? So more the current, the strength of the magnetic field will be larger. So that's why, because of course, it's just a bubble of plasma. It's a ball of plasma, not a bubble. It's just a ball of plasma, highly intense and high temperature plasma, highly energetic plasma. Because of the free flow of electrically charged ions and electrons, magnetic field of the sun is produced. Okay, so the changing magnetic field of the sun govern many aspects of solar activity. Now I am introducing something called as changing magnetic field. So this magnetic field will not remain constant, and this change in the magnetic field, coupled with the differential rotation of the sun, is responsible for the creation of solar activity. And most importantly, from this image itself, we can clearly say that during the quiet periods of sun, when the sun is quiet, there are very small number of coronal mass ejections and solar flares. And visual inspection itself tells you that when the sun is very active, so this part is called as the active sun, and this part, this image, can be referred to as the quiet sun. So when the sun is very active, it itself conveys a message that there will be a lot of eruptive phenomena, like again CMEs, solar flares, etc., etc. Right. So the changing magnetic field. Now what we are trying to make a flow. We have to understood what is sun, and then we have understood many properties. Like I said, sun emits energy in the form, primarily in the form of two different manifestations. One, particle nature, which is very small in comparison to the electromagnetic. The second is the electromagnetic energy. So we get the light, and we also get particles, right? Now, if that is the case, then we should understand more in more detail about these two forms of energy, obviously, right? So what are the two forms of energy? Particles and electromagnetic radiation. So we have entirely dedicated a couple of lectures only to understand the electromagnetic nature of energy coming from the sun. How much is it coming, in which way it can be categorized, etc. That is done. Now we are looking at the particle nature. Right? There is a constant stream of particles escaping the sun's gravity, which we call as the solar wind. And apart from that, also there are these events which are not a constant phenomena, which are called as the coronal mass ejections and solar flares. And these events are entirely related to two things. One, the sun's magnetic field, and the differential rotation of the sun. Okay, so these two things combinedly govern the many eruptive phenomena which appear on the sun, or which are thrown into the interplanetary space. Right. Now let us try to understand the true nature of the sun's magnetic field. The solar interior is composed of highly conducting and highly ionized plasma. Right. So you would not deny that solar interior can be having a lot of heavily ionized plasma. So when these particles are moving, they generate a current, and this current will subsequently lead towards the formation of a magnetic field. So magnetic field thus generated out of this movement is frozen into the plasma. This frozen in is a condition in plasma physics. If you are curious, you can read about this frozen in condition. This magnetic field is frozen in the plasma itself. Now, the solar dynamo, which is located in the interior, where the plasma, which is rotating, generates electric currents and converts the plasma motion into magnetic energy. Okay. The likely location of this high shear zone, the likely location of the solar dynamo is the high shear zone between the convective zone and the radiative zone. Okay. This is where it is getting created. Now, how intense is the magnetic field? What are the typical parameters associated with this magnetic field? Sun has a very strong magnetic field, which is approximately 1,000 times as strong as the Earth's magnetic field. Okay. And Sun's just like the Earth's magnetic field, Sun also changes magnetic polarity. This changing magnetic polarity is what we are referring, or is what leads towards the solar activity. Okay. So, this change of polarity happens over a period of time, and this period of time seems to be of the order of 11 years. So, this is again the same thing, solar cycle. Okay. Now, how do we know this is 11 years? So, we know this information about the changing polarity in by observing the sunspots. Sunspots, we have already seen what are sunspots. Sunspots are the visible features on the photosphere, which are very strong in magnetic field and at the same time comparatively existing at a lower temperature with respect to the ambient photosphere. Okay. Now, these sunspots give away this information that change of magnetic polarity is happening over every 11 years. So, every 11 years it happens. Okay. Over the period of last 5 billion years, approximately 5 billion years, this has been happening. The observations have been existing only for the past few hundreds of years, the sunspot observations. But this sunspot, the number of sunspots that appear will grow towards the solar maximum and will decrease afterwards. So, this keeps happening every 11 years. So, few hundreds of years of observing sunspots have revealed that this periodicity must have been existing. Right. Maybe when the sun was very young, the activity period may have been different. Okay. But that's an elaborate discussion. Okay. So, for 11 years, the leading sunspots will have the same polarity, which is north, and then for the next 11 years, they will have the opposite polarity, south. Okay. We will talk about the polarity, but for now, let us just take this as a fact that for 11 years, the leading sunspots will have a north polarity, and for the next 11 years, it will have a south polarity. So, if you combine these two things, it will be in terms of sunspots polarity reversal, it will be 22 years. So, the magnetic field disrupts the normal processes on the surface of the sun. Okay. Now this is where it actually starts getting very interesting. Okay. So, the magnetic process, magnetic fields, which magnetic fields I am talking about? I am talking about the magnetic fields of the sunspots, which are very strong. Okay. So, the magnetic field disrupts the normal processes on the surface of the sun, and as a result, when these processes are disturbed by the magnetic field, the convection, which is bringing the energy to the top, to the photosphere, gets obstructed. Okay. So, granulation is a normal process. Strong magnetic fields hinder bubbling of the hot gas, which is basically referring to the convective processes which are bringing mass to the top along with the energy. And when this process is hindered, so the amount of gas or amount of hot plasma that reaches this region decreases. Okay. Or effectively, the temperature of this region decreases. So, this region becomes cooler in comparison to the surroundings, which actually means that this region will appear darker in comparison to the surroundings. That's why we get to see the sunspot. So, it's like one thing leading to the other. So, the magnetic field will first emerge out of the sunspots, magnetic flux lines, and they will hinder the convective processes, and this hindrance will subsequently lead towards the lowering of temperature near the sunspots. Okay. So, if you have strong magnetic fields, you will have cooler temperatures. So, is it the fact? Is it the inference that we are going to draw in this? Let's see. Okay. So, magnetic field, some more additional information about the magnetic field. So, much like the Earth, the Sun has a magnetic field that closely resembles the magnetic field of a bar magnet. Okay, much like the Earth. So, Earth is also Earth's magnetic field can also be approximated towards to a bar magnet. Okay, Sun also has a magnetic field that closely resembles the magnetic field of a bar magnet. So, the nature of solar magnetic field influences the solar activity, including the sunspots. Okay. The solar magnetic field changes over time due to the sun's rotation. So, as a result, during the solar minimum, the magnetic field consists of straight flux lines. Okay. So, what you see here is the sun. If it is a bar magnet, let us consider a bar magnet. You have the north and you have the south poles. Okay. So, the flux lines will appear something like this. Okay. So, the magnetic flux lines will always diverge away from the north pole and converge towards the south pole. This is what we know. The magnetic flux line is an imaginary line along which unit north pole will keep moving, right? So, in this way, this is how a typical bar magnet will look like. So, inside the magnet, of course, the flux lines are traveling like this. So, we can extrapolate. So, the direction will be exactly opposite. So, this is exactly what is shown here. So, in the beginning, let's say during the time of, so it's like solar minimum to maximum. Maximum is when you have a lot of disruptions in the magnetic field, and then again minimum, right? So, during the solar minimum, when the magnetic flux lines are kind of straight and parallel inside. Okay. Now, what will happen is as the time progresses, okay, as the time progresses, because of the differential rotation, equatorial regions of the sun are moving much faster in comparison to the polar regions. So, the magnetic lines of force along will be pulled towards, this is from west to east. Okay. The magnetic lines of force are being pulled towards the east in comparison. So, they are more elongated or they are more stretched in the equatorial region in comparison to the polar region. So, as the sun differentially rotates with the faster rotation occurring at the equator, the rotation rate can be tracked by the movement of the sunspots. You can, with simple instruments, you can see the sunspots and you can measure the amount of time it takes for a particular sunspot to cross the visible disk watching from the earth. Okay, can be tracked from watching the sunspots at the equator. It around takes 25 days, and for the sunspot to complete one full rotation between, and around 29 or 30 days at the higher latitudes. Higher latitudes. Okay. So, this causes the magnetic field lines to distort. So, this is what I was talking about. The magnetic field lines are not straight and parallel anymore. So, they are being stretched. Okay. So, as the time progresses, even with more time, what happens? This distorted magnetic field lines will become even more complicated. Over a period of time, these magnetic field lines become so distorted that they become twisted or they intertwine. Okay. So, this twisting of magnetic flux lines actually creates or causes sunspots. Okay. Now, the polarity change that I was talking about. So, sun's activity period is a part of the relatively consistent cycle of 11 years. So, at the peak of each maximum and minimum, the polarity of the magnetic field flips. This signals the start of the next stage in the cycle. So, the same change in polarity occurs to the Earth's magnetic field, but this change of polarity takes several millions of years in the case of Earth, but for the case of Sun, it happens every 11 years. So, what you can see is every 11 years, the North Pole becomes the South Pole, and exactly opposite happens over the next 11 years. Okay. So sun's activity increases and decreases during this period of 11 years. So in the image on the right hand side, what you see are two large sunspots. You see a region, an entirely black region, in which the temperature is very less, maybe by 1000 or 1200 Kelvin, and in comparison to the surroundings, of course. But then this region has a very strong magnetic field. So when the sun is more active, more sunspots are visible on its surface from the earth. By recording and analyzing the number of sunspots, it is possible to gain an insight into the activity of the sun itself. So if the results are recorded over longer periods of time, the cyclical nature of solar activity becomes evident, and the predictions on future activity can be made. So this is the only prediction that is possible right now, because we know to some extent that the whether the next solar cycle is going to be less active or more active. We don't know it for sure, but we can make some models. Some modeling efforts can tell you to what extent it will be. The solar activity will be intense in the next cycle. And then we know approximately which year we are going to have more number of or maximum number of coronal mass ejections or solar prominences. Okay. So for hundreds of years, solar activity has been mapped by the observation of sunspots. Okay, so this is how it. This is the last, uh, not the last. This image is ending at a period of, let's say, 2005 or 2007. We are now in 2025. So this image shows how the number of sunspots. So on the y-axis, you have the number of sunspots. On the x-axis, you have the year. So you see that in 1975, the approximate number of sunspots that were seen on the visible disk were maximum at, let's say, 20. It kept on increasing, and it reaches almost 200. 200 sunspots on the visible disk. This is when you get maximum number of coronal mass ejections occurring from the photosphere. And then again it decreases. It reaches a minimum of nearly 20 at 1987 something, where again the minimum number of sunspots are 20. It again increases, it again decreases. So this periodicity is what I am referring to. This periodicity approximately spans over 11 years. So starting from 1974 to 1985 is approximately is 11 years. Right. So it is clear from this data that over a number of years, the cycle of activity or the solar activity repeats itself. Okay. And this is what, so this period of time is the quiet sun, and this is an active sun. Okay. So by observing the very preliminary prediction that we can do at this point of time is that by observing this, you can say 2005, if 2005 is the minimum, 2006 is the minimum, then you're going to get 2017 as probably the next minimum, things like that. Okay. But that is, I mean, that is a very basic type of prediction. And we also call the strength of the solar cycle. If the number of sunspots, if the maximum number of sunspots, it need not be always 200. There have been times when the number of sunspots were much larger, and there have also been times during the maximum, the highest number of sunspots were far too less in comparison to this, right? So it is not entirely understood how the solar activity is can be predicted, or it's not entirely understood what exactly decides the solar activity, the cycle, the duration of the cycle, or the strength of the cycle. Okay. But a very preliminary forecast can be made that solar activity at this particular year, on this year, probably will be of this magnitude. Okay. So by observing this, one may be able to predict when the next solar maximum will occur. Okay. Now let us look at sunspots in more detail, so that we are going to explain the occurrence of this coronal mass ejections based on this, right? Now, in order to understand sunspots, we need to have two things in mind. One, the differential rotation, and the solar magnetic field. So these two things combinedly are responsible for the creation of sunspots. So sunspots are cooler regions of the surface of the sun, and they are about 1500 Kelvin less in temperature than the surroundings. Okay, it is still, I mean, we've written still 4500 Kelvin. What does it mean? It means it is still at a very large temperature. Okay, so sunspots, you see on the left, this image clearly shows all the granulation, all the upwelling of mass, and then the clear boundaries of the convection cells are distinctly shown in this image. Then you have this huge feature which appears on the sun, which is the sunspot. Okay. So the diameter, the typical size of this diameter is a few 10,000 kilometers. You see, now you put the diameter of the Earth to comparison, you will see that it is huge in comparison to the sunspot is huge, right? So they always appear in groups. Okay, and this sunspot was even observed by Galileo, and the sunspots persist for periods ranging from hours to months. So it's not a feature which will just appear and disappear. They remain on the surface for periods starting from few hours to several months. Okay. Now the central region is called as umbra, which is the dark region at the center, and the lighter region surrounding the umbra is called as the penumbra. Okay. So sunspots are associated with strong magnetic field. In a pair of sunspots, one sunspot will have the leading sunspot will have northern polarity, and the other sunspot will have south polarity. So with this information about the sunspots, we will continue our discussion in the next lecture, learning how exactly sunspot become the windows of the solar prominences. All right.